this is the largest chapter I prepared for you. But again, I didn't have enough time. So most of the content actually are from my very good friend, Professor Randy Geiger from Iowa State University. I only modify a little bit, all right? Anyway, this is also a chapter I'm really proud of myself and Professor Geiger, because we are teachers instead of preachers, okay? Yeah. We are not preachers because for most of the professors, they teach analog IC design. They only show you, oh, this is op-amp, what type of op-amp, what type of current source. Usually they focus too much on equation derivation. To myself, I think that is simply time wasting. Okay, to help the students most, we need to explain the operation principle, the logic thinking, in much detail. Yeah, with as much detail as possible. Yeah. Anyway, for op-amps, I'm really happy with Professor Geiger's lecture notes, because I hope we can brush your brains to have totally different logic thinking about op-amp. I mean, if you attend the classes of the other teachers, or even you read the Bibles, analog IC design by Professor Razavi or Allen, I don't think they can have such kind of very good insight in such kind of op-amp design. Okay, so this may be the most important chapter I would like to share with you. Yeah, op-amp, the most fundamental building block for analog IC design. From the very beginning, I will have some kind of preview for the op-amp design history, what is the applications, and how to survive the op-amp design in low voltage, with low voltage processes, and what is the fundamental skill to design such kind of op-amp, and then yeah, how to enhance the performance of such kind of op-amp, and for emerging processes, I mean with very, very low supply voltage, how op-amp design survive? How can such kind of op-amp design survive? Yeah, we have quite excellent recommendations from Professor Geiger. Actually, op-amp used extensively, especially in analog IC design. Okay, for most of the analog circuit, they are far from ideal, but op-amp is exceptional. Yeah, it is very close to the ideal case, to be honest. And from the very beginning, we have a very popular op-amp, LM741. Actually, I guess even till now, we still use such kind of very old op-amp in our industry. Okay, for example, LCD driver. They apply many op-amps to drive the vertical knife, the horizontal knife. Okay, and when humankind created, I guess more than 40 years ago. Okay, so if you look at digital chips, if you have digital chips 40 years ago, right, even from the best company Intel, or even from ARM. Oh, ARM 40 years ago, I don't think ARM existed. Okay, but 40 years ago, yeah, Intel was already founded. If you have chips in that era, I think you will throw all of them into the trash can, because for nowadays applications, such kind of digital chips, they are already out of date. Okay, the operation speed, the power consumption is too bad. All right, but even till now, humankind still use such kind of very old, yeah, maybe in your grandparents' era, we still use such kind of analog chips. Yeah, so it means what? The lifespan of analog chips is usually much longer than digital counterparts. All right? But I need to point out that I would like to teach you about the open design to fit special purpose for your special purpose applications, right? We wouldn't like to teach you how to design a general purpose open. What's the definition? What is the difference between special or general purpose application? For general purpose, it means one for all. Okay, I design one open. It is good enough for all the applications. Forget about it. We are humankind. All right? But for commercial product, yes, we have some, the so-called special purpose open. But it is not one for all. To the most, you can say, hey, one for many. But nothing is free. You need to pay for it. Pay for what? Usually, very high power consumption, very expensive, very complicated in circuit design. It doesn't make any sense for your on-chip application. For your on-chip application, usually we design one for one. Okay, you have a large analog circuit. You have many kind of sub-circuit. For one sub-circuit, you may need to design one or quite a few op-amps. Each one may be different from the others. Okay, so usually we teach the students that, and also that is the usual case for you. One op-amp for one specific sub-circuit. That's it. To fit the operation of your specific circuit, it means what? You can reduce the complexity. You can reduce the difficulty very, very much than the general purpose one. Okay? Again, don't expect yourself can design some kind of one for all circuit. No, it never existed on Earth, especially for analog IC design. So some of the history in 1964. Wow, right now it's already right more than 50 years ago. We have very popular the first linear means analog, exactly the same for definition. Okay, that is the first analog IC on Earth. Yeah, mu A702. But we are talking about mu A, right? Yeah, after some years, we have this. Okay? Yeah, it has only 12 transistors for such kind of general purpose op-amp. All right, it is designed by Bob Witter. Hey, Witter current source, Witter blah blah blah. They are artists. They are not only engineers. No, you need to respect them even more. Why? Because in the past, it's really hard to fabricate. So they need to try their very best to reduce the chip area, especially the number of devices. So usually for their own design, many of the devices were reused. It means one for many functions, one device for many functions. Okay? And it means what? If you look at in the past, they are quite generous. They will show you the detail of the equivalent circuit. Okay? From transistor, resistor, capacitor, even they will show you the size. How much the resistance is, how much the capacitance is. Wow, they are really generous. Because in the past, nobody could compete with them. They will show you everything. Nowadays, no detail. Okay? Only function blocks in the chip. Oh, we have this, and we have that, and connection, blah, 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 blah. And what's inside? Nobody would like to tell you. Yeah, because according to the rise of China, they duplicate everything. Okay, so it's really upset. No sharing at all. Western countries need to protect their IPs from Chinese. Yeah, even for us, the same. But even with such kind of black boxes inside, Yeah. Right now, I think TI is still the best company for analog chip fabrication and design and fabrication. The others maybe just like National Semiconductor, analog devices, linear technology, blah, blah, blah. They are still among the top of the top for analog field. Anyway, even though they don't show the detailed content, but they still decap the chip of the others. Okay, they try to decap layer by layer and some kind of micro photos. And right now, I think they apply maybe some AI to automatically recognize the equivalent circuit. Okay, and after they get the exact circuit, they will duplicate it and with some kind of modification. They how can I say? They are not worried about the violation of any kind of IP because they have cross licensing. Okay, I sue you, you sue me. Nobody wins. Only the lawyers. The lawyers get a lot of money from that. So after suing each other, all the companies will go for bankruptcy. all the money to the lawyers. So finally, for the big companies, they settle down the system. Okay, you don't sue me, I don't sue you. You can copy mine, I will copy yours. That's it. All right, that's it. But to slow down the process, they still they wouldn't like to show the detail. Okay, that's it. For such kind of big companies, they have a branch, a department focused on reverse engineering. Okay, to see what happens in the other company. That's it. Okay. You can see, even they show you the detailed circuit, usually, especially for new engineers, for junior engineers, they don't get anything. Because it's really complicated to understand what's inside. Each device is designed for multiple purposes. It is reused again and again. It makes the circuit much simplified than the traditional one. So you need to have some kind of very good knowledge, experience to figure out the original circuit. Okay, anyway. After 1 year later, wow, the same guy create already micro, mu A709. So a few years later, the most popular one was invented. Anyway, from 12 to 14, okay? Of about the same chip size, and it is from Fairchild. I told you already, Intel, National Semiconductor, analog devices, many of them actually, the co-founders were from Fairchild. And this is some kind of practical view for you. The real chip look like this, and this is some kind of pin assignment. You can see, wow. The major issue is it has inverting input, non-inverting input and output. But as a circuit, it needs power supply. Okay, so it needs VDD and ground, or VDD and VSS. I don't care. Usually to simplify the circuit symbol, we only draw something like this: positive, negative, and output. That's it. But don't forget, it consumes power, right? At least it needs another 2 pins to connect it to the VDD and the ground. That is the real circuit, at least 5 terminals, 5 pins. Okay, before the real design, let's focus on the applications. Oh, it has a lot of applications. If you take out op-amps from the market, I can promise you almost nothing will be functional. Not only your mobile phone, it has maybe hundreds of thousands of them inside. Even you go to the toilet, right? When you get closer, wow, it will rush. It will flash some current some water, and after you go out, it will flush more current to clean the toilet, right? How to make it? Oh, piece of cake. It has something like this. Usually, it needs to have a pair. Yeah, photo LED, LED to or IR LED. Yeah, to inject some light on humankind. If you go closer, then the reflected light will make the photo sensor or photo detector conduct more current. More current means higher voltage. So with op-amp, you can set how much voltage to be the definition close enough. It means, oh, somebody go over there, right? So the first flush of the water. Yeah, for what? To make the surface weight. Otherwise, your piece will be stick to the surface of the ceramic. Yeah, it always smells very bad. And even after that, you flush more water, it doesn't help too much. Okay, so from the very beginning, yeah, a little bit water to make the surface, the ceramic surface wet. Yeah, and all the piece will go down to the drain. And after that, flush a lot of water. Okay, anyway, that's it. That is a very simple idea. Okay, but there's another joke. In the ghost month, okay, we have ghost month. Yeah, the 7th month for our lunar calendar. If you, in the night, you go to the toilet, you see somebody, get closer, and make peace, right? Make water, then go away. Wow, nothing happened. It means what? The IR won't be reflected by this. What kind of humankind? It is not any kind of humankind because it is cold. Okay, it has no temperature. It doesn't reflect any kind of IR back to the photo. If you don't have such kind of scientific sense, yeah, people or girls get in and out, you won't sense anything going wrong, right? But after studying this, well, hey, why? This guy won't reflect IR, IR back to the sensor because it is cold. Okay, it is a ghost. Anyway, for switching power supply, you need many of the op-amps. Now, I don't go for such kind of detail. I only tell you it is applied to almost every kind of analog circuit. Okay, and for such kind of remote sensing, okay. For example, in chemical plant, usually in the oven, we need to sense the pressure, the temperature, blah, 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 many kind of physical quantities, right? But it's too dangerous. If you would like to get in to check temperature, that is too much, okay? So usually we embed our sensor inside the chamber, okay? And then send all the signal back to the control center. But with such kind of remote sensing, the signals will be interfered, will be jammed by interferences or noises. Okay, so how to make the signal as clean as possible? We need differential sensing. It means two signals with opposite polarity, positive, negative. Okay, differential sensing. That is really important. After go back to the control center, yeah, because op-amp is supposed to amplify the difference of the input signals instead the common value. Okay, so if for those two signals, they are jammed with exactly the same noise or interference. Yeah, I'm here, you are there, but you are jammed with noise, I'm jammed with the same noise. So after taking the difference, the interference, the same interferences or the same noises will be filtered out, will be subtracted out from each other, right? Then you can get the clean output, very good, with very good quality. So for remote sensing, we need differential signals. Okay, and how to amplify the difference, we need the help of op-amp. Anyway, op-amp is almost everywhere. That is some kind of general design philosophy. In theory, op-amp needs to operate downward all the way to DC. Okay? And it means if you have an op-amp to help you amplify 100 times, blah, blah, blah. Even you have DC input 0.1 by 100 means 10 volts output. Okay? That is from the very beginning, by the nature, op-amp needs to operate all the way down to DC. But for such kind of DC operation, it means in the past, one of the traditional skill we called AC coupling or capacitor coupling, it cannot be applied here. Because inside the op-amp, usually it has more than one stages. Okay? So for the first stage to the second stage to the third stage, I don't care how much stages you have, you cannot have such kind of capacitor coupling, because for capacitor coupling, the DC cannot penetrate from the input to the output. It will be blocked, right? So you need to apply direct coupling. It means my output directly to your input. But what is the problem? Why we need such kind of AC coupling in your microelectronics? Usually it means my output DC bias doesn't fit your DC input bias. Okay, so with such kind of capacitor coupling, we can separate both of them. Only the AC signal can penetrate to the other side. But right now, it is not applicable because we would like DC to be functional. Okay, but again, you need to face the same condition. If the output DC bias doesn't fit the input DC bias of next stage, what you can do? You need something in between, right? We call it lever shifter. Yeah, this one. To shift the output DC of the previous stage to the input DC level of the next stage. Okay? In this way, we can make DC functional for such kind of op-amp design. All right? And then for op-amp, the major issue, we call it input offset voltage. It is not 0. So if it is 0, it means what? We need identical transistors. Okay? But anyway, how to make the transistors exactly the same with each other? For BJT, their IS, their beta, their early voltage, or for MOSFET, their threshold voltage, their W over mu COX. Okay, all of them needs to be the same. And lambda for channel length modulation. All those parameters need to be the same to make the transistors exactly the same with each other. Okay, that is in theory. In practice, no. We can only try our very best to make them about the same, but not exactly the same. Okay, this is some kind of review from microelectronics. Yeah, in theory, what is ideal op-amp? Again, it only helps you to amplify the difference of your inputs. Okay, with infinite gain. We call it differential mode because this gain is used to amplify your minus, your positive minus your negative, and amplify by ADM, right? Differential, because the difference of your V plus and V minus. And we hope the gain is infinite. That is for ADM. Yeah. Anyway, for all the gains you discussed in the past, right now, or even into the future, if we don't talk about what kind of mode, we only focus on differential mode. It means we only focus the gain to amplify the difference between your two inputs. Okay? From the past into the future. But in practical situation, we have common mode. So for example, again, we have positive 0.1, negative 0, or positive 10.1, negative 10. The difference is the same, right? But what is the definition for common mode voltage? The average. Okay, so here the average is around 0, and there the common mode voltage is about 10 volts. Okay, in theory, we hope we only amplify the difference. So 0.1 and 0, 10.1 and 10. In theory, the output should be exactly the same, right? But sorry for that, in practice, they won't be the same. So we hope ACM, common mode gain, will be 0. Never mind how large the common mode voltage is, we hope they don't have any kind of impact on your output. But in practice, no, forget about it. And this is, the other one is common mode rejection ratio, 共模矩式比. It means what? We hope this one very large, that one very small. So how to assess, how to judge the design, the op-amp design is good or not? Because we would like to amplify the difference very much. We hate to amplify the common mode voltage, right? So we compare your ADM to your ACM. This one as small as possible, that one as large as possible. In theory, infinity and 0 means infinity. Very good. But that is only in theory. How about in practice? Okay, let's go for our real lives. See? For ADM, usually 60 dB. I mean, 1,000. Good enough. For some specific design, it can be 10,000 or even 100,000. Okay, for one op-amp. But nothing is free. You need to pay for what? The bandwidth will become really, really small. Okay, usually the larger gain means the smaller bandwidth. Please keep this in mind. Unless you change your process, unless you change your structure, with the same structure, we know that gain bandwidth product will be fixed. The larger gain means the smaller bandwidth. Okay, nothing is free. Pay for it. And finally, for this one, for practical concern, differential mode gain are usually around hundreds to thousands. That is the usual case. And how about common mode gain? It is not 0, usually around 1. Okay, so it means what? If it is 1, oh, you need to be very careful, right? 0 or 1, 10.1. The output from here to there, you will get, if it is 1, okay, you will get 10 volts. Wow. The impact is still very huge. Okay? So, how to judge your design, your op-amp design, according to gain? Your design for gain is good or not? Again, we design ADM by ACM, right? And usually, we hope your common mode rejection ratio, because we would like to reject common mode according to differential mode. We would like to reject it as small as possible, right? So that is the definition for common mode rejection ratio. Reject common mode. Okay. Anyway, enhance differential mode, reject common mode. Usually hope your design can be better than 60 dB. I mean in magnitude. Okay? Yeah. The final issue, but the most important issue is this. VOS, input offset voltage, because we hope if they are exactly the same, you showed your input, your positive to your negative, we hope you get 0 for your output, right? That is only in theory. How about in practice? Even you apply the same voltage to your input, I promise you your output won't be 0. Okay, it has something. So how to make your output exactly the same as 0? You need to apply some kind of offset to your input. That is the so-called VOS, input offset voltage. So in practice, how much? In theory, it should be 0 here. Okay. In practice, sorry for that. If you don't pay attention to your design and layout, I promise you more than 2 to 5 millivolts, sometimes more than 10 millivolts. But again, our differential mode amplifier, our gain is more than 1,000, right? Right? So if you have 5 millivolts to the input, how much is the output? Already 5 volts. So for your 0.80 micron process, the supply voltage is only what? 1.8 volts. 5 volts means what? Your output is already saturated. That's it. Saturated means what? It doesn't work anymore for you. It is saturated over there. Never mind what kind of voltage you apply to your input. It doesn't matter. The output is already saturated. Okay? But I need to warn you again. VOS, we only talk about the absolute value. It is positive or negative, usually with 50%. If nothing wrong, 50% of your chips after fabrication will get positive VOS. 50% of them will get negative VOS, according to random mismatch. Okay? So even you short your two inputs or apply the same voltage to your input, I promise you, for such kind of open loop application, yeah, you don't have any kind of feedback to from the output to the input. I promise you, your output is either positive saturated or negative saturated to the ground or to the VT. That's it. Okay? I promise you, if you go to our library, our how can I say, warehouse, 库房, at first floor, you borrow as many op-amps as possible, apply VDD and VSS or ground, then short the input. I promise you, only 2 possibilities for such kind of open loop applications of op-amp. The output will be either positive saturated or negative saturated. Anyway, VOS for our analog IC design is the major challenge for you guys. Okay, especially for high-end application. Such kind of VOS, according to very high gain, I mean ADM, it will cause you a lot of problem for your output. Okay, so how to reduce such kind of VOS is a major challenges. Nowadays, with good layout or very complicated calibration, auto calibration, on-chip calibration. Anyway, human guys can make it around microvolts. Okay, if you are interested, maybe you can refer to one of my also very good friends, Professor Kofi Makinwa from Nigeria, but he taught in TUT or DUT. The Delft University of Technology. Okay, yeah, that is the so-called European MIT. Okay, yeah, that is the best technical university in Europe, but it is in the Netherlands. Yeah, he migrated from Ethiopia, Nigeria. Sorry, a very black guy to the very white country, and till now, I guess he's still the best for temperature sensor design. Okay, if you would like to focus on any kind of temperature sensing, Coffee Lab is the best, because for each PhD, yeah, when I visit Coffee Lab, he told me the company needs to support 50,000 euros. Okay, euros instead of US dollars for each PhD candidate. Wow, it's really expensive. Okay, for performance evaluation, for example, this is some kind of non-inverting amplifier. In the past, you will see from microelectronics, it will say the output, the gain between your output and input look like this, right? Piece of cake. Okay, how can you make this? Under the assumption the op-amp is ideal, it means the gain is infinite, you don't have any kind of VOL, blah, blah. I don't care, I don't mind. Okay, I would like to tell you that if you take the non-infinite gain into consideration, the gain is not infinite. Okay, after derivation you will get this. Okay, then what is the error term? Sorry. Here, 1 is perfect, and this is error term. All right, I would like to tell you, for example, if the gain is around 10, then to obtain error less than 1%, your differential mode gain should be larger than 1,000. And this is the reason why in practice, ADM is usually the hundreds or even thousands. Okay, 1% in error, not so accurate, to be honest. Okay, 1% error according to ADC or DAC, it means the accuracy is only 6 to 7 bits. No much, yeah, no better than that. Okay, 7 bit to 6 to 7 bit, really bad, right? But even that, you need 1,000 gain. Okay, yeah, the gain should be 1,000 or more to make the error less than 1%. And for the others, we have slew rate. Slew rate, it means what? For the output, for such kind of unity gain buffer, it means your output is connected to your negative input, right? Then in theory, your V out will be exactly the same as your V in. All right? Under such kind of configuration, how fast you can change your output voltage? Because your input is changing. Up, yeah. Anyway, you need to follow your input, right? Especially, what is the most challenged one? For example, if you have such kind of pulse input or square wave like input, right? Wow! For the rising edge or the falling edge, they are perpendicular to your zero or your low or your high levels. That is only in theory. Yeah. If you apply such kind of ideal waveform to your input, how about your output? Sorry for that. They don't follow it. It will go like this and that. Okay? So, for the rising or the falling edges, how fast it can go? That is so-called slew rate. Okay? So, what is the physical limitation for the slew rate? It means the major issues related to slew rate is how much parasitic capacitance to the output, including yourselves, you and the load. Okay, both have such kind of parasitic capacitance. And then to charge it or to discharge it, I out. Okay? The output current of your final stage dominates the slew rate. It means what? If you would like to make it as fast as possible, then you need to design a very large I out. But nothing is free. You need to pay for what? To generate very huge I out, it means the W over L for your final stage should be really large. And also, for large I out, it usually means what? Large power consumption. Okay? So, to increase slew rate, you need to sacrifice your chip area and your power consumption. Okay? And this is the first lesson you can learn from your op-amp design. Usually for students, new engineers, they would like to make the output waveform as ideal as possible, so they would like to have very good slew rate. Wrong. Wrong decision. Because too much chip area, too much power consumption usually means nonsense for your real design. Because op-amp is only one of the many, many blocks in your analog chip, right? For each op-amp, if you would like to enhance the slew rate, you need to sacrifice a lot of area and power. It doesn't make any sense. So as a good enough engineer, how much the slew rate should be? Again, good enough. That's it. According to your specification, according to your applications, only if the slew rate maybe 30% better than the specification, I think, good enough. At most 2 times larger, good enough. Why? We need to have, why not exactly the same as your specification? Because process variation. You need to have some kind of tolerance for your process variation. Usually, yeah, positive, negative, I think peak to peak, 30 to 40%. Okay? For such kind of process variation. So 50% more or even double for slew rate. Good enough. No more. Otherwise, you will waste too much power and chip area. And the other one is settling time. Again, what is the definition for settling time? Okay, here. If you apply such kind of step function from 0 all the way to 1, right? But to our output, we have slew rate limitation, and after you reach the maximum, you have such kind of damping, usually. Okay, so what is the definition for settle time? Okay, or settling time, it means the time for your output to settle down within 10% of the final value. Okay, within 10%. So you can see, hey, look here. Oh, okay, this is the settling time. No, because positive, negative, usually 10%. Okay, the spikes. The peak is over positive 10%. So this is not your settling time. And how about this one or that? No, because for the value, right, it still exceeds negative 10%. So finally this one, because after this, all the value is within positive, negative 10% of your final value. Okay, that's it. So this is the definition for settling time. Anyway, a few minutes more. Okay? And then, how to improve the linearity? Oh, to be honest, you can see that is still too, how can I say, too idea. You can see positive saturation, negative saturation, right? So we only operate here to amplify your signal. You don't amplify your signal here or there because it's already saturated. As I mentioned before, it doesn't work anymore for you. We focus here. But even for this, the slope, the higher slope means the larger gain. Okay, but anyway, I would like to tell you, it is not true because to the most, it will look like this. In this region, well, it is not linear at all, right? Here and there. So you may say, hey, I focus on this in the middle, as you like. But if you would like to get even more linearization, okay, there is a very important idea for you. The second important idea for this chapter, you need to design fully differential op-amp. Okay? Because for op-amp, we have differential input, positive and negative already, right? So what is the definition for fully differential? Two differential outputs. So you have differential input, two differential input, two differential output. That is the so-called fully differential. Okay, why we need it? To enhance your linearity. I'm a teacher instead of preacher. Okay, I need to tell you all the truth, all the correct concepts. For example, this is your positive output. If you have only one, then you have y plus. Okay, and x is your input. I mean, the difference between your positive and negative input. Okay, x means the difference between them. Then we hope what? For linear amplification, we hope you have y equal ax. Oh, that is really good, but it is never be true. Usually you have something like this. A1x is what you need for linear amplification. Okay? And A0 means what? Offset. And for all the others, they are distortions. 失真. You hate them. But how to reduce such kind of distortion? Differential operation will be good for you. If they are fully differential, it means what? You have positive output. You have also negative output. Okay? Negative output with the same function, but yeah, you are negative, you are positive, I'm negative. So you have this. Okay? And then how to take the output? Again, the difference. Because from the input, we amplify the difference of your input. So for the output, we also take the difference. Okay? So the final output will be the difference of your y positive minus your y negative. So congratulations. Bingo. First of all, no offset. Secondly, you can see the even order harmonics are all erased, right? So at most, you have only third order harmonics. But for real applications, you look at the spectrum. Offset here. So that is A0. Then A1. The one you would like to have. And then A2, and then A3, and then A4. Usually, it degraded very soon. From the fundamental to the second harmonic, third harmonic, all the way, decayed very soon. So right now, according to fully differential operation, no A0. No offset, congratulations. No A2, no A4. What do I mean? Because A3 usually is much less than A2, right? So the overall distortion according to A1 will be substantially reduced. Congratulations. much less distortion for differential operation than single-ended operation. Okay, if you take only one, we call it single-ended. Okay, if you take both, we call it differential. And fully means both input and output. That is the terminologies. 这就是我们的定义。Okay, so I'm really proud of myself and Professor Geiger because we are teachers instead of preachers. We don't preach you believe our gods or your God. No, no. We show you the truth. We show you any kind of correct logic thinking to help you survive in your own futures. Okay? Anyway, anyhow. All right. That is okay. Yeah. That is the end of today's class. In next week, I hope I can finish chapter 5 for open design. Even though I have totally 300 pages, but for some kind of not so important slides, I will skip. Otherwise, I will teach open for 5 weeks. It doesn't make any sense. Okay, we need to go further. That is our life. We need to keep on going and teach the other important content. Okay, so hopefully next week or at most 2 weeks later, I need to finish open design. And how about the other slides? Read by yourself. If you have any problem, just contact me. Okay, thank you.